So far we've talked about a few mathematically formal machines that we've been able to use to solve quite a few problems. And when we talk about problems, we're talking about languages. One of the things we showed at the start of the course is that often when we want to answer yes or no to a question, we can formulate that as answering yes or no to whether a string is in a language. And it's been good for us so far because we've had these simple machines, finite state machines to start with, that we could use and build to answer those questions. But we got to a point where we had a lot of questions that we could prove that we were unable to answer using these machines. So we took that machine and we expanded it by giving it a stack, and we came up with the push-down automata. And that was great for a little while as well, because we could answer even more questions than we could before with that machine. But as we've seen with the language AN, BN, CN, we've now reached a point where we can't answer some questions with that push-down automata. And one of the other things that's problematic is we've gotten to a point where we have these machines, but we can't reprogram them. Every time we want to solve a problem, we have to build a whole new push-down automata or finite state machine. So it would be good if the next thing that we came up with was not only more powerful than the push-down automata or finite state machines, but was also able to represent computers in the way that we often use them. We're able to write a program, load it onto this machine, and have it run. But it would still be fantastic if it was described simply enough that we could reason about it mathematically in the same way that we have with the finite state machines and the push-down automata. Now, if you've heard of the man Alan Turing, and you probably have because of the new Imitation Game movie, but you'll know that he came up with a lot of fantastic mathematics around the World War II era. And one of the things he gave us transformed the field of computer science, and it was the mathematical model called the Turing Machine, and we still use it today. What I need you to remember for this video is the definition of a push-down automata, and that is it's just a finite state machine that we've given a stack to, and it can fiddle with that stack. And the second thing I need you to remember is that this language can't be accepted by a push-down automata. So we've proven that using the pumping theorem for context-free languages, and so we know that this formalism, the push-down automata, can't handle that language. It can't answer the question of whether a string has an equal number of A's, B's, and C's, one after the other. So let's not go through the full formal theory, but look at the underpinning of why a push-down automata can't accept it. So the way a push-down automata deals with AN, BN is as it sees A's, it shoves them onto the stack. So our stack ends up being a record of how many A's our machine has seen. Then once it starts seeing B's, it just compares the top of the stack and says, is there an A here? And then when it sees a B in the string, it simply crosses them off one by one. Now the reason it can't then compare an equal number of C's afterwards is that by the time it's finished this process, the stack is empty, that record is gone. But it seems like we should be able to deal with it pretty easily because we should just be able to go through and look and just compare as we're going. And then when we're finished with looking at the B's, just go, okay, is there now an equal number of C's? But because of the formalism of the stack, that we can only look at the top element and we have to pop it off to look at the next one, we end up lost. Now we can straight away see that if we had a second stack, we could do it. We push all of the A's on first, and then each time we come along and we see a B, and we cross off an A, we push a B down onto the second stack, etc. So once we've done, this stack is now empty, and this stack has a record of how many B's have been seen, and then the C's come along and compare to that. Now, this is enough already to show us that a push-down automata with two stacks is definitely more powerful than a push-down automata, because we've just shown a way to accept a language that we know cannot be accepted with push-down automata. And this idea of being able to exchange the data structures that our finite state machine has access to suddenly changes the power of the formalism is what will lead us to the Turing machine, because it's just a push-down automata with a different data structure. So let's imagine that the push-down automata had a double-ended queue. So it has this pipeline and it can push things on at either end. Now, if we wanted to deal with A and B and C n, we could do that quite easily. As we see the A's, we shove them in at one end. Then when we start seeing B's, we start crossing off A's from one end and shoving B's on the other end. Then when we see the C's, we go through and clear them out. So we can see there is no requirement for having two data structures for something that is basically a finite state machine with a data structure to be able to deal with more languages than the push-down automata can. So that's what leads us into the Turing machine, because we end up with something almost like a double-ended queue, and that's called the tape, the infinite tape. So let's talk about the Turing machine. Let's imagine that our finite state machine with a data structure, instead of having two stacks or a double-ended queue, it instead had a tape that was infinite in length, so it spread out to the right and left in all directions, in both directions forever. And that tape was made up of single cells, each of which could contain one symbol. So it's essentially like a string that can expand in any direction. So most of this tape is blank, except for the input string that we'll put onto this somewhere, and anything that we've written as we go along. So the idea here is that we will have something that is still just a finite state machine, like before. It has a set number of states. And instead of being given its input string arbitrarily floating off on the side, it gets given the input string written down onto the tape. What the machine also has is the ability to look at one spot on the tape at a time, and it does that through something called the tape head. So don't worry too much about what the tape head is. The idea is just that the machine is able to look at one spot at a time, and it can move which spot it's looking at. So it's kind of like having a push-down automata with its little stack, and being able to move up and down the stack and look at things without having to pop everything off. So the informal definition is that our machine, when it's sitting in a certain state, it looks at what symbol is on the tape at the position of the tape head, and then it uses a transition function, just like the ones in the finite state machines and the push-down automata, to go, I am in this state, and this is the symbol I'm looking at, to define a transition into another state, and then to potentially modify what's written here. So maybe it can write a dollar sign down or something. And then to also decide to move this tape head one spot to the left or the right. So now the tape head might be here or it might be here. So at this point you might be able to see how if we could accept A n, B n, C n with a double-ended queue, then it's pretty trivial that with a tape that can extend in either direction and access to any point on that tape, we should also be able to accept that language. Now I'm not going to give an example here, but it might be worth thinking about it. And if you can't figure it out, that's fine, because it'll be covered in lectures with Nasimul. So all you need to know is that we can take a push-down automata, rip away its stack, and give it an infinite tape that it can look at one position at a time, and slightly change the definition of the transition function, and we end up at what's called a Turing machine. And what you're going to find out later is that that Turing machine is the most powerful formalism we have yet to this point. And you're going to learn a lot of useful things that we can do that. And most importantly, you're going to learn a lot of useful facts about what we can do with modern computers based on showing what we can and can't do with these Turing machine models.